This is lesson 71 on shift registers. Here's an example of a 4-bit shift register made up of 4D flip-flops connected serially, where the output of one shift register becomes the input to the next one. Notice there's a common clock and a common clear. So on the rising edge of the clock, the data in on this leftmost flip-flop gets moved to Q3, and at the same time what used to be in Q3 gets shifted into Q2, and at the same time the old Q2 goes into Q1 and the old Q1 goes into Q0. So the important thing to note is that they all go in parallel. Here is an example of what's called a 4-bit ring counter. It looks like the 4-bit shift register we had, except instead of data coming from the outside in the leftmost one, we connect Q0 back in, and that becomes the input to D. So everything gets shifted from one to the other. So if they all started out at 0, nothing would happen. So what we do is we take the clear signal and we connect it to the set input of this rightmost flip-flop. The others get cleared, so when the clear reset goes high, we'll end up with a 0 in Q3, a 0 in Q2, a 0 in Q1, but a 1 in Q0. Then on the next rising edge of the clock, what used to be in Q0 goes into Q3, and the others get shifted. So let's see what this would look like. We would start out then with a 0, 0, 0, 1 for Q3, Q2, Q1, Q0. And then on the next rising edge of the clock, this Q0 goes into Q3, so we end up with a 1, 0, 0, 0 for the 4 bits. On the next rising edge of the clock, the Q3 bit gets moved over, everything else gets moved around, so this bit looks like it just moves along. On the next rising edge of the clock, it'll go to Q1. On the next rising edge, it'll go to Q0, and then it will cycle back to Q3, Q2, Q1, Q0. So in this ring counter, this 1 just cycles around, moving from one flip-flop to the next. This, if you look down what Q3 looks like, it looks like a pulse here, a pulse here. So you got a pulse train in each one, but notice they're offset by one clock cycle. So you end up with really what's called a 4-phase clock here. Here's an example of what's called a Johnson counter. It looks something like the ring counter, but instead of connecting Q0 into the D of the leftmost one, we take not Q0 and move it around here. So this one we can start with zeros in everything. So the clear goes into all of them, so we'll start with a 0, 0, 0, 0. But since Q0 is 0, not Q0 will be 1, which means there's a 1 sitting here. So let's see what happens with this one. Here is the Johnson counter. We'll start out with 0, 0, 0, 0, but now not Q0 is a 1, so a 1 will be sitting here. So on the next rising edge of the clock, the 1 will go into Q3, and the others get moved over 1. What's going to happen on the next rising edge of the clock? Well, this Q will move over 1, but we still have a 1 here because Q0 is still 0. So we'll get 2 1s moved in. Still 0 here, so there'll be a 1 sitting at D here. So they all get moved over again. On the next clock, you'll have a 1, 1, 1, 1. But now Q0 is 1, which means that not Q0 is 0. So now you got a 0 sitting here at D, so what's going to happen? You get a 0 moving in here, and everything moves over. On the next rising edge of the clock, this 0, you'll have a 0 coming in again because you still have a 1 at Q0. You still have another 1. So you move 3 zeros in. This is still 1, so you got a 0 coming in, and you're back to 0, 0, 0. And this pattern repeats then. This is called a Johnson counter. Let's look at one more example. Here we have what looks like this 4-bit shift register, but now we'll take Q0 and we'll exclusive OR it with Q3. And we'll see that this produces a kind of random number generator for the 4 bits, Q3, Q2, Q1, Q0. Let's take a look at how it would work. Suppose we start with a 0, 0, 0, 1. I do that by making the set again like we had before. So the clear would make zeros for these 3 and a 1 here. So we'll start with 0, 0, 0, 1, which is the hex number 1. And now what do we have? Well, we have a 1 in Q0 and a 0 in Q3. Well, the exclusive OR of the first and last bit here, 0 exclusive OR with 1 is 1. So we got a 1 sitting at D, so on the next rising edge of the clock, that 1 will get moved to Q3, and everything gets moved over 1. So we'll end up with a 1, 0, 0, 0, which is an 8. Now we have a 1 and a 0. The exclusive OR of that's going to be 1. So we'll end up with a 1, 1, 0, 0 on the next clock cycle, which is a C. You got a 1 and a 0 here. The exclusive OR is still 1, so we'll end up with a 1, 1, 1 as these get shifted over, which is an E. Here's a 0 and a 1, so this exclusive OR will be 1 again. So we'll have 1, 1, 1, 1, which is an F. But now we've got a 1 for Q0 and a 1 for Q3. Well, the exclusive OR is 0, so now you'll have a 0 coming into Q3. These 3 bits get shifted over, which is a 7. So you look at sort of a random occurrence here. We got a 1, 8, C, E, F, 7. Let's see what happens next. 0 exclusive OR with 1 is 1, so we'll get a 1, 0, 1, 1 as these zeros and 1s get shifted over, which is a B. Now you got a 1 and a 1. Exclusive OR of that's 0, so we got a 0, 1, 0, 1, which is a 5. Notice we haven't got any repeats here. 0 exclusive OR with 1 is 1, so we're going to be a 1. Let's start over here. A 1, 0, 1, 0. 0 moves over, and the 1 moves over, and the 0 moves over, which is an A. Now you've got 1 exclusive OR with 0, which is a 1. So we have a 1, 1, 0, 1. The exclusive OR here, and the 1, 0, 1 moves over. That's a D. Here we have a 1 exclusive OR with 1 is 0. 1, 1, 0, which is a 6. Notice we still have no repeats. 0 exclusive OR with 0 is 0, and the 0, 1, 1 moves over. That's a 3. 0 exclusive OR with 1 is 1, so we get a 1, 0, 0, 1. That's a 9. Still no repeats. 1 exclusive OR with 1 is 0. 1, 0, 0 moves over. It's a 4. What's left? You see 0 exclusive OR with 0 is 0, so we have a 2, and 0 exclusive OR with 0 is 0, and we're back to 1 where we started. So we go 1, 8, C, E, F, 7, B, 5, A, D, 6, 3, 9, 4, 2. So this is sort of a kind of pseudo-random number generator where the sequence we get looks like no particular order, sort of a quasi-random number generator.